Okay, so we want to extend the idea and the power of the fundamental theorem to calculate the area between two curves. So to illustrate this, let's look at our paste here of theorem 1. So what we've been doing is treating the x-axis as a curve and the area above it and below some function was calculated by the integral of f(x) dx. Well, if I've got two curves, and this is even more useful in terms of when you start getting into engineering and things like that, or economics and things that we can apply applications to. If I want the area between this curve and this curve, then I'm just going to take the integral from the lower bound where my area starts, the vertical line where my area starts, and the upper bound vertical line, and take the top. Now this is really important. The function that's on top has to be here minus the function that's on bottom. So essentially when we use the x-axis, well that's like if we created h of x equals 0, well that's just like y equals 0. That's the x-axis. So if this was f of x, we were calculating the integral from a to b, so we were calculating this area. Well, we were really doing f of x minus h of x dx, but h of x is 0. So that simplifies, I've got a frog in my throat all day today. That simplifies to f of x dx because h of x equals 0. And f of x is whatever. Now, let's go the other way where we said maybe f of x was down below, and this was a and b. And remember we said if I calculate the integral from a to b of f of x here, I get a negative area if a is the area. When I calculate the integral, I get negative a. Well, this all makes sense now because remember this is, let's call this h of x again. Well, now following this rule, I have to take the curve that's on top over that interval, and this time h of x is on top. So by this rule here, I want the integral from a to b of the top function, h of x minus f of x dx, because h is on top. So that's the integral from a to b of h of x, which is 0, minus f of x dx. So to calculate that area between, I have to take the opposite of this. So I end up with the integral from a to b of 0 minus fx, which is just negative f of x dx. And that gives me the actual area, which is the opposite of this, which is negative a. So of course it's going to give me positive a. Now let me bracket that just to make it a little clearer. Okay, so if we start with the function above, it's got to be above for the entire interval we're interested in. So obviously f of x is above g of x, beginning at a and ending at b with no intersections in between. So I can calculate the shaded area by taking the integral from a to b of whatever the top function's rule is minus whatever the bottom function's rule is, dx. Okay, so we call that the area between two curves. Okay, that's pretty powerful. Okay, so we've really already discussed this when the x-axis is involved. So here we're just treating this like g of x equals 0. So let's take and answer this question. Now they've given us the rule for f of x. It's x squared minus 2x. So for part A, they're asking for the area between the graph and the x-axis, which is g of x equals 0, between 1 and 2. So if you look at 1 and 2, the top function is 0. So we have to think of this as the integral from 1 to 2 of g of x, which is 0, minus f of x, which is x squared minus 2x dx. Okay, so you don't have to get this fancy all the time. You can just say, oh, well, since the curve that I'm calculating area for is below the x-axis, I'm going to take the opposite. So that equals integral of x, I'm just going to simplify this. If I distribute the negative, I would get a positive 2x. 0's gone. Distribute the negative, I get positive 2x, and then the x squared becomes negative, so we'll just reverse the signs. From 1 to 2. Okay, that's the same thing as negative integral from 1 to 2 of fx dx, which we said, since it's below the x-axis, is how to get the area. You have to negate it. Okay, so now let's go ahead and follow through and calculate this part. What we're calculating is area from 1 to 2. So this really corresponds to A1. So now taking the integral, I'm going to get integral of the 2x is going to be 2x squared over 2 minus x cubed over 3, running from 1 to 2. Simplify that. X squared minus x cubed over 3, running from 1 to 2. Substitute. So I'm going to get 2 squared minus 2 cubed over 3 minus, now the 1 squared minus 1 cubed over 3. Okay, so that's going to be 4 minus 8 over 3 minus 1 over 3. I'm going to spare you the details. I think that comes out to be 2/3. Let's see. This will be 9/3 minus, yeah. Okay, so roughly equal to all right, now let's look at B. This corresponds to going from -1 to +1. So I've got this separation here. I can't do it all in one integral. I want to calculate A2 and add A3. Okay, so that's going to be the integral from -1 to 0 of f of x minus g of x, which is 0, so I'm not going to expand on that anymore. So it'll be x squared minus 2x dx. This is A2. Now A3 is going to be the integral from 0 to 1. And this is of negative f of x because it's 0 minus f of x. So 0 minus x squared minus 2x dx. Okay, so let's get A2 calculated. This is going to be x cubed over 3 minus 2x squared over 2, which is just x squared, running from negative 1 to 0. So that's going to be 0. When I plug in the 0 for these, I get 0 in both cases, minus, now we'll plug in the negative 1. Negative 1 cubed over 3 minus negative 1 squared. So that equals the opposite of negative 1/3 minus 1, which is 3/3. So it's the opposite of negative 4/3. So that would be positive 1 1/3. Okay, so that's A2. Now for A3, got a real estate problem here, which is this. We already simplified that. Okay, so that's going to be the other way around. We're going to get 2x squared over 2, so x squared minus x cubed over 3, running from 0 to 1. So that's going to equal 1 minus 1/3. Two-thirds. We already calculated that. So, all right. Or did we? Well, we calculated the other side of it and it looks symmetrical. So, yeah. All right. So now to add this all together, I want 4/3 that I got for A2 plus the 2/3 that I got for A3. Okay, so the area between the curves x squared minus 2x and the x-axis between negative 1 and 1, the total area is 2. All right. Let's move on to when our curves don't cross, and then we'll get into when they do cross. It's a little easier when they don't cross. Okay, any questions? Just go ahead and interrupt. I know you guys are pretty pretty quiet usually about the questions, and best case scenario is because you don't have any. But if you do and you're not asking them, I really encourage you to go ahead and just chime in. All right, so f of x is going to be a line with a slope of 1/2 and a y-intercept of 3. And g of x is going to be this upside down parabola, opens down. And what we want to find is the area between the line and the parabola from -2 to 1. So this is a straight interpretation. This is just a direct result of Theorem 1. So we're going to go and create the integral from, oh, I jumped ahead one slide too many. Get to you later. This is when curves don't cross. So this is basically asking us for the integral from -2 to 1. And we get to use just f of x minus g of x because f of x is exclusively above g of x during that entire interval. So we go from -2 to 1, and that's 1/2 x plus 3 minus -x² plus 1 dx. So I'm just distributing the negative across here, and I'll simplify this to x² plus 1/2 x, and I've got a 3 minus a 1, so that's going to become plus 2. Okay, so that's going to equal x³ over 3, and then this will become x² over 2, and there's already a 2 down there, so I have to multiply those together. So this will become plus x² over 4, and this last one will just introduce x to the first over 1. So we got to run that integral from -2 to 1. Okay, so this ends up being, when I substitute the 1 in, 1/3 plus 1/4 plus 2, minus, when I substitute the -2 in, I get -2³ is -8. -2² is +4. And then 2 times -2 is -4. Okay. All right, and if you tally all of that up, you should get an area of roughly 8.25. All right, so that's the area that's shaded here in blue. Now we've got a little extra complication if we've got, we're asked this question where there's intersection points involved. This is just saying find the area bounded by f of x equals 5 minus x² and g of x equals 2 minus 2x. Well, I'm going to have to take a look at the graph. So while I'm at it, I'm going to go ahead and pull up my graphing calculator. And I'm going to go into y equals. And I'm going to put my two bounds because without an orientation of a graph, I may not know which graph is on top and which one's on bottom. Now, it's no problem finding the intersection points because you just set the two functions equal to each other and solve. So we'll do that in a minute. But I want to go ahead and put both of these. I'm going to put f of x in y1. So I'm going to put 5 minus x² and I'll put g of x 2 minus 2x into y2. And that way, when I go look at the graph here, and I can do a trace, and that tells me I'm on y1 equals 5 minus x squared, and then I can jump down to the other one and see that y2 is the 2. So it tells me which one's which. And if you don't see the window the way you want to see it, you can play around with your zoom. Zoom standard's usually a good place to start. And then if you don't like it from there, you can go, this is 10 by negative 10, positive 10, negative 10, positive 10. You can go in the window and adjust that. Okay, so what I'm interested in are the intersection points. Well, I've got two options. We'll get back to the calculator in a minute. I need to know where they share a point, and that tells me the bounds for my integral. So I'm going to set f of x equal to g of x and solve. Okay, because of course that's where they're equal, right? They both share negative 1, 4, and 3, negative 4. So we're going to get 5, when is 5 minus x squared equal to 2 minus 2x. All right, I'm going to set it equal to 0. So I get 0 equals x squared minus 2x. 2 plus negative 5 is negative 3. So they've made life easy because we can factor this to x minus 3, x plus 1. That tells us that the x's where this is true is when x equals 3 and x equals negative 1. So that's how we got our negative 1 and our 3 as the bounds. That means I need to integrate from negative 1 to 3. And f of x is on top during that whole interval. So we want the integral from negative 1 to 3 of f of x, which is 5 minus x squared, minus g of x, which is 2 minus 2x. So that's the integral we need. Simplifying that result, I'm going to get, so 5 minus 2, so it's going to be 3, so it's going to be negative x squared. Actually, I like to write, when x squared is negative, I'll put it. So we end up asking for the integral from 2x plus 3 minus x squared dx. Okay, so that's going to be 2x squared over 2, which is just x squared, plus 3x minus x cubed over 3, running from negative 1 to 3. And I'm not going to go through all that detail, but you should get something roughly equal to 10.667. Okay, remember, just substitute the 3 into all this, then subtract, substitute the negative 1 into all this, and it should pop out that. Now let's get back to the calculator. We do have some more power in the calculator to find the intersection points for us. So if I want to go and say, I'm sorry, you got to go to second calc, and option 5 says intersect. So you can either scroll down to 5 or just punch 5 in and hit enter. And it's asking for the first curve of the intersection. Since there's more than one intersection, the one you're interested in is the one you want to get closest to. And then it knows there's only one more curve to choose from, so it jumps to it and says, is this the other guy? Yeah, and then still don't know what the guess means. Just hit enter. Seems like, so it tells us right away, straight off, that the x coordinate of the intersection is -1 and the y coordinate is 4. So that's our lower bound, the x of -1. We can go get the other intersection point. Just make sure that you choose your curves closer to the point of interest. All right, so its x is 3. So that gives us the upper bound of 3. And its coordinate is 3, -4. Okay, so the calculator's got that ability, or you can set the two functions equal and find where they intersect. But you're already going to want to use the calculator to help you decide, or some form of a graph to help you decide which function's on top. You could do it algebraically just by getting the output and seeing which one's greater on that interval. Okay, so that's when they just ask us to find the area bounded by these two. Then I have to go find the intersection points and figure it out. Now, if we've got intersections that cross, so what are we going to do here? In this case, they would like the area bounded by F. And F is on top during some part of it, but then F is on the bottom during the other part. So in this case, we're going to split it up and say I need the integral for A1 from -2, but I can't go all the way to 3 because it flip-flops top and bottom, and I always have to start. So I'm going to end at 0. And that's going to be from F minus G. And then A2 is going to be from 0 to 3. But this time it'll be G minus F because G is on top during that interval. Okay, so let's just go ahead and calculate A1 and A2. So F minus G is going to be x squared minus x minus 2x. So if I take minus x and minus 2x, that becomes minus 3x. Okay, so that's x cubed over 3 minus 3x squared over 2, running from -2 to 0. Well, the 0 is going to make both terms 0, so that's going to do nothing. And then I have to subtract. And then when I plug the -2 in, I get -8/3 minus -2 squared would be 4, so that'll be 3 times 4 or 12 halves. So that equals negative Just pop that in a calculator and you should see you get 8.6 repeating. Okay, and then we also have to calculate A2 from 0 to 3, and this time it's going to be G, so it's going to be 2x minus F so that'll be the 2x, so that'll be 3x minus x squared running from 0 to 3. Now this time it's the other way around. The 3 is going to matter, but when I subtract and insert the 0, it's going to be 0. So my answer is going to be 3 times 3 squared, so 3 times 9 over 2 minus 27 thirds minus 0. So 27 halves minus 27 thirds. So we're talking 4.5. So I got to put my 4.5 plus my 8.667. So 13.167. Okay. I thought I wrote a 7 there. I guess it disappeared. Okay, let's get back to the calculator. Let's say I've got f of x is equal to e to the negative x squared, and g of x is x squared minus 1. Okay, and our goal is to find the area bounded by these two curves. Well, I don't have any context at all here. So I'm going to go to the calculator. Don't need those anymore. And we'll put e to the negative of x squared. So there's my first graph. And then g is x squared minus 1. And then I'm just going to do a zoom to a standard and see what I see. All right, I can tell there's definitely an area bound between them, so it's a little bit far away. So since this is 10, 10, 10, 10, I'm going to go into my window and give myself a little better perspective and maybe start at -4 and end at +4. And don't change the scale, but for y min, I'll also use -4 and the upper bound +4. Now if we hit the graph, that's a little better. Okay, in this case, we need the intersection points to know where our integral starts, and we can trace and see that the on top is the y1. So what this is going to end up being is the integral of f of x minus g of x the whole way through. But we don't know these yet. So let's go ahead and get those. So we're going to go back and do a second calc intersection. So move over here a little bit. All right, so negative 1.13, and I'm going to round that and make it a 1. And probably going to be, it looks very symmetrical, so I'm guessing the upper bound is going to be 1.131 on the positive side, but let's be 100% certain. Like a roller coaster. And indeed it is, positive 1 point. Okay, kind of a mess because it's got 3 decimal places. So don't fret it. I'm going to show you a friendlier way to go about it. All right, so I'm just distributing the negative. That's all I've got left to do there. So what we want is e to the negative of x squared minus x squared plus 1 dx. Back to the calculator. Okay, we could calculate this doing the integrating it and running it from negative 1.131 to positive 1. Your calculator also has, where is that? If I go to math and the 9th option, FN int, it'll allow me to put lower bounds and upper bounds in my function and whatever I'm integrating with respect to. So in this case, we're going from negative 1.131. Just hit the up arrow to get to the upper box. 1.131. I hit enter too soon. I didn't want to hit enter. I wanted to arrow over to this part and put in our e to the negative x squared, then right arrow to get off of the exponent, minus x squared plus 1, and arrow over to put our x here. It's the only variable. Okay, so I took the time to figure out what had to go in the integrand, but then I can go in here and use this to do some of the grunt work if, for something, a function that's this complicated with these points being decimals, that kind of be a lot of work. Okay, so we get 2.8755. We round that to 3 decimal places. We'll say 2.876. Oops. Okay, so that's gotten the calculator involved, and we're calculating areas between curves. Again, pretty powerful. I'm going to stop recording here.